Okay, so those are vectors. We're now going to move up one level and deal with matrices. So these, so just again, just to introduce language, which is probably not totally familiar to you all yet, because we have not really started quantum mechanics properly in class. But those vectors represented states that, for example, an electron could be in with respect to its spin. Now, spin is an example of an observable. It's a type of angular momentum, so you can make measurements of it. One of the postulates says that for everything we can observe or everything we can measure in quantum mechanics, there is some operator corresponding to that observable. And furthermore, as we'll see in this notebook, these operators come sort of along with these special values, which are called eigenvalues. And those eigenvalues represent all of the possible values that could actually be measured. So we're going to see that the spin operator that we're going to be dealing with, which is called SZ hat. So operators will wear hats. So this is the operator for the spin component of angular momentum along Z. It comes with two eigenvalues, plus 1/2 h bar and minus 1/2 h bar. And so that's just an intrinsic property of the operator. And what we can always do with operators in quantum mechanics is we can always find a matrix representation of those eigenvalues, of those operators. In fact, so one of the things we have to do if we want a matrix representation of our operator is we have to choose a basis. And a basis is in a sense like a coordinate system. So oftentimes in linear algebra, we will think about like our Cartesian basis, where we have a basis vector which points along the x direction. And we have a different basis vector which points along the y direction. And we have a different basis vector which points along the z direction. But that's a basis, and any point in Cartesian space can be represented in terms of the basis vector along x, the basis vector along y, and the basis vector along z. So in quantum mechanics, it's very similar. This space that we're dealing with spin is not a Cartesian space, even though we have z components. So these basis vectors that we're dealing with are a little bit abstract. Nevertheless, we have a basis vector which represents spin pointed along z in the up direction. And we have a basis vector which represents spin pointed along z in the down direction. And any type of spin that you could ever realize, whether it's pointed along z or somewhere else, can actually be built in terms of those basis vectors. So those two basis vectors we have already seen. 1, 0 is the basis vector for spin up z, and 0, 1 is the basis vector for spin down z. And any spin can be built as a combination of those two basis vectors. So that's our basis for spin. That's the basis we'll choose. And what I have done here is shown you the matrix representation of the SZ operator built in that basis. So I've chosen my basis 1, 0 and 0, 1, and now I will use that basis to build this matrix. And how that's done is something that we will definitely see in lecture. I don't want to belabor the point now. If we find out we have time at the end, we can certainly talk about it. But for now, we're just going to focus on building this matrix in Numpy and working with it a little bit. Okay. So the syntax to build this matrix is very, very similar to the syntax for building our vector. The difference is now my first row, which up here is 1, 0, has 2 columns, right? Instead of 1 column like the chi-ket. Okay, so my first row I'm going to write as 1, 0, and that's going to correspond to this row up here. And my second row I'm going to write 0, -1, corresponding to this row here. So overall, the S sub z vector, or sorry, the S sub z matrix, traditionally people write in the following way. H bar over 2 out front, so this is sort of like the constant, which is multiplying every element of this matrix, and then within this matrix we'll write 1, 0, 0 minus 1. This is totally equivalent, by the way, so this is exactly the same thing. I have my black marker, which was, thank you. Totally the same thing as h bar over 2, 0, 0 minus h bar over 2, right? This simply means multiply every element of your matrix by this number, h bar over 2. Just people will traditionally write this matrix with the h bar over 2 factored out in front, so I want to show you that notation. We can define that matrix in NumPy in the following way. H bar over 2 times NumPy array, this stuff. We need to give a value to h bar. Python doesn't know what h bar is. I'm going to use a unit system which is called atomic units, and in that unit system the value of h bar is actually 1. And that's a unit system I like a lot. Dr. Woods is not a fan. This is just a rift between theorists and experimentalists. Theorists love atomic units, experimentalists hate it. But anyway, I'm running the show today, so we're using it. I mean, it's a lot more convenient than some number times 10 to the minus 34, I think. So anyway. What's that? Yeah, this is atomic units of action. So action is a real quantity. It's an energy times time quantity. Anyway, so this is still a unitful number, but the units are atomic units of action. Yeah. Okay, so let's go ahead and define this matrix. So you can copy the syntax here, but I'm going to just ask you to try to type it by your own hand. And then after that, go ahead and write the code to print S sub z. And then below that, so below this hashtag, write the code to print the shape of S sub z. And I keep saying S sub z, but the variable name that I'm using here is SZ. So you should define SZ, and then print SZ, and then print the shape of SC. Sure.
Yeah, make them work for it. Where does your problem session meet?
We're going to meet here on Friday, actually.
Okay. At what time?
8:40. Okay. So I think everybody got, at least as I was scanning, it looked like everybody got the right array. 0.500 minus 0.5, and then the shape is 2 by 2, 2 rows, 2 columns. Everybody good with that? Okay. So as I mentioned, right, we have defined these basis vectors, ket alpha and ket beta. So, so the choice for that basis was not accidental. This is a very nice basis for this matrix S sub z. Why is it a nice basis? Well, these vectors, chi alpha and chi beta, are what are called eigenvectors of this matrix S sub z. And what that means, okay, so if I actually, hopefully I've picked, so if I in general have a some matrix and I multiply that matrix by some vector, okay, I get a new vector on the right-hand side. Okay, so how do I determine what that vector is? Well, I'm going to kind of use the same same kind of pattern of operations as I use for multiplying a row vector by a column vector, except for in this case I've got 2 rows, right? So I have to do 2 different sets of this operation where I take this row and multiply it by this column. And so that is going to result in another column vector which has 2 rows. So the first row of my resulting column vector is going to have the value A times E plus B times F. And then the second row is going to have the value C times E plus D times F. Okay. So I have some new column vector. And typically, and if I just want to think about, again, if I want to think about this in kind of a Cartesian space where my initial vector EF looks like the following. So let's say that that's my vector EF. After I multiply EF by this matrix, well, who knows what's going to happen? I have a completely new vector. It is quite likely that this vector has changed in length compared to EF. Right, so what, by the way, the length of EF, if I want to talk about the magnitude of this vector, so I'll call it the V, the vector has length like this, kind of this Pythagorean sum here. That's the length of this vector V hat. So when I multiply this vector V hat, these elements, by this matrix, 2 things can happen. The length of the vector can change, but there's this other property associated with vectors. Right? They have length and they have direction. Magnitude is the same as length.
Oh.
They have direction.
They have direction, yes, direction. Direction and magnitude. So the other thing that can change is the direction. So you should think of the process of matrix vector multiplication as a process of rotating and stretching or compressing your vector. So the resulting vector, I don't know where it's going to go because I don't know what this matrix looks like, but it might, for example, go like this, right? I might stretch it out and rotate it this way. That's one possibility. I might shrink it and rotate it this way. That's another possibility, okay? So all kinds of possibilities. A very, very particular possibility is that all I do is lengthen it, but don't change its direction. And another really particular possibility is all I do is shrink it, but I don't change its direction. So imagine then that second scenario, shrink it but don't change its direction. I multiply this vector by this matrix, and all that happens is it gets shorter, but it points along exactly the same direction. The other possibility, if I lengthen it, but it points along the same direction, just like that. So these two scenarios where I either shrink it or lengthen it, but the direction doesn't change, this will only happen when this vector is an eigenvector of this matrix. Okay? So an eigenvector of a matrix M, so we'll call eigenvector V hat of matrix M satisfies this relationship. M multiplied by V hat is equal to a number, lambda, times V hat, right? This number lambda could be larger than 1, could be smaller than 1, but V hat does not change direction. Multiplication only changes magnitude. Okay. So that's a very special scenario. Right. Typically what happens, you'll get a completely new vector, points along a completely different direction, and has a different length. There are some cases, by the way, could you have the other scenario where the length doesn't change but the direction does? Raise your hand if you think, yes, that's possible. Yes, that's possible. Great. This is called unitary rotation, by the way. If you, there's special matrices called unitary matrices. They will rotate vectors. They will not change their length. Those are also quite important in quantum mechanics, but we will probably not study them. Okay.
So this would come up like if we're talking about vibrations and things like that, where vibration can move in one direction. Right?
Mm-hmm.
That's what bonds do.
Yes. Yeah.
Dr. Foley will do the vibration dance later this semester.
I will absolutely do the vibration dance later this semester. So here we have a set of eigenvalue equations with the operators, and we're going to show that the matrix representation of SZ and these basis kets will also satisfy these eigenvalue equations. But basically what these eigenvalue equations say is I have this state, ket alpha. If I act upon ket alpha by this operator SZ hat, I get chi alpha back multiplied by h bar over 2. So I have lengthened this state chi alpha by the value plus h bar over 2. And then this statement down here says if I act upon state chi beta with SZ hat, I get chi beta back. And I have lengthened it by the amount minus h bar over 2. You may say to me that no, that means it points in a different direction, and that's quasi-true, but it is parallel to its original vector. It's pointing in the opposite direction because it's been multiplied by a negative number. It's still an eigenvalue, though, I promise. That is true. Okay, so let's see if we can demonstrate that this holds. Okay, that these eigenvalue equations hold. So I'm saying that this is the relationship for these operators. When we build this matrix SZ, it's a matrix representation of this operator in a particular basis, and we should still be able to observe the same relationship. So what we're going to do, we are going to take the product of that matrix SZ with ket alpha, and we are going to see if that product yields ket alpha multiplied by h bar over 2. And we are going to do the same thing with SZ on ket beta and see if SZ multiplied by ket beta yields ket beta multiplied by minus h bar over 2. Okay. And we'll first sort of just inspect the results and see if it works, and then we can add a layer of sophistication where we perhaps compare it directly to h bar over 2 times the corresponding ket. Okay, so this is another kind of multiplication. NP dot will also support this multiplication where we have the matrix on the left-hand side and the ket on the right-hand side in this way. So I'm using this nomenclature again, SZ underscore ket underscore A for SC multiplied by ket alpha, and I'll use SC underscore ket underscore B for NP dot SZ ket beta. So let's give it a shot.
I think this is like, I don't know how many times I've seen it, but I feel like it really clicked when you explained it.
Oh, good. I'm so glad.
Oh, I don't think we asked. Has anyone ever used Python before? Anybody did any coding? Any kind of coding? R? C++? I don't, no one uses C++.
No, people use C++. Don't hate. C++ is an example of a compiled language, so it is
It's
somewhat more cumbersome to use, but it's awesome.
Mathematica. Has anyone ever used Mathematica? MATLAB? Origin? Igor? Okay, just checking. Is there any other options?
There's a million. Julia, Fortran, Spark, Rust, Ruby. It goes on.
Anaconda? That's a Python thing.
Yeah, it's a Python thing. Does anybody need more time for this?
Green flags.
Okay. Okay. So what I got for SZ ket A is 0.50. And what I got for SZ ket B is 0 minus 0.5. So let's sort of think about the statement that I made. Right, so we had ket chi alpha is equal to 1, 0. And then we said SZ hat, the operator acting on ket chi alpha, is equal to plus h bar over 2 times ket chi alpha. So then the matrix vector equivalent of this is that if I have SZ, the matrix, multiplied by 1, 0, which is chi alpha, the vector, I should end up with plus h bar over 2 times 1, 0. Okay? And we are working in a unit system where h bar is 1, so really this is the number plus 1/2 times 1, 0. So this would be equal to 0.50. So that seems to work. SC ket beta, right? Let's just really quickly do that. SC hat, the operator, acting on ket chi beta, is equal to minus h bar over 2 ket chi beta, and the matrix vector representation would therefore be equal to minus h bar over 2, 0, 1, which is equal to 0 minus 0.5. Okay. So a totally equivalent way, so we could just sort of look at this and look at our notes and say, okay, this works out, right? There's a variety of different ways that we could do this to to sort of test or have the computer do a little bit more work to do the inspection for us. One way, really quickly, is I could, in this print statement, take the result of this multiplication, right, and then subtract from it what I expect, right? So for this particular one, I'm multiplying ket alpha by SZ, and I expect it should be equal to plus h bar over 2 times ket alpha. So what I could do then is I could subtract from this thing h bar over 2 times ket alpha. And if the two are the same, what I should get is print 0, 0. And at the same time, I could, from SZ ket B, subtract from it minus h bar over 2 times ket beta, which would be the same thing as plus h bar over 2 times ket beta. And then that should also be 0, 0. So I do, in fact, see zeros across the board. There are even more elaborate ways I could do this. For the interest of time, let's skip that for now. I think we probably have time for just the very next piece. Yeah. Any questions before I move on to the next and maybe final block for today? So then the last block I'm going to talk about today is on Hermitian matrices. So so one of the things about the operators corresponding to observables in quantum mechanics are that they are so-called Hermitian operators. Hermitian operators are also called self-adjoint operators, which means that if you take that operator and find its adjoint, it will be the same. It will be unchanged. So the matrix representation of that operator, if I take the adjoint of that matrix, it will be the same. So the adjoint, we've defined it once already. We've defined it for vectors. It is really the same thing for matrices. So can anybody remind me how I defined the adjoint of a vector earlier?
You can use your notes.
We can use our notes. We can even consult the notebook where those notes exist.
Talking about when you transpose it?
Yes, transpose, and it's two operations I'm going to do. I'm going to transpose, and I'm going to take the complex conjugate.
Good teamwork.
Yes. Okay, so when I transposed a vector, all of the rows became columns. Same thing happens with a matrix. So I have matrix A, B, C, D, and its transpose, right? This is row 1. That's going to become column 1. All right, T for transpose. So row 1 is going to become column 1 of my new matrix. Okay, row 2 is going to become column 2 of my new matrix. Okay, so that's the transpose. You'll notice the diagonals have not changed. upper diagonal of this matrix was A, and the upper diagonal of this matrix is still A. The lower diagonal of this matrix is D. The lower diagonal of this matrix is still D. But what has changed is the off diagonals have flipped. Okay, so that's the transpose. That takes care of this piece. The complex conjugate, each of these elements, what I'm going to do is I am going to take the complex conjugate of each. So A star, C star, B star, D star. Okay? So, what you can see in this particular case, in order for, okay, so this is our adjoint matrix. So I'm going to write here adjoint. And then the original matrix down below is this one. So in order for this thing to be Hermitian, we have to say the following. A must be equal to A star. D must be equal to D star. B must be equal to C star, and C must be equal to B star in order for this to be Hermitian. Typically, this means that your diagonal elements need to be real numbers. And if your off diagonals are complex, then the upper off diagonals need to be the conjugate of the lower diagonals. So that is basically the other thing. There is also implied in this a pretty high degree of symmetry in this matrix. One of the advantages, just from a computational standpoint, is operations with these matrices tend to be faster because computers can exploit that underlying symmetry to not redundantly do operations. Anyway, what else do I want to say about Hermitian matrices? An important property of Hermitian matrices is that the eigenvalues, so we just learned about eigenvectors and eigenvalues very briefly. We're going to see more when we complete this notebook later this week. But the eigenvalues associated with this matrix must be real numbers. And that's important because when you go into the lab and you make a measurement on angular momentum or energy or position or whatever, you are not measuring like my energy is 3 minus 4I. You are measuring a real number for the energy. You're measuring a real number for position. You're measuring a real number for angular momentum. So these eigenvalues associated with operators and quantum mechanics correspond to the things that it's possible to measure in the lab. Therefore, they must be real numbers. So Hermitian operators have that property. We're going to do one final thing. We are going to test. It's already written for you. We're just going to run this piece of code. Oh, wait. No. Sorry, there's one other thing we actually have to write. So we're going to compute the adjoint of SZ. And then what we're going to do is this is the sophisticated, who will have the computer check everything for you. We're going to check that element by element, the adjoint of SZ is equal numerically to the elements of S. And we'll see that if they're all close, the computer is going to print true. And if they're not, if even one of them is wrong, the computer will print false.
And all close means what?
Yes, element by element. They are all the same number to within a round-off error. So it's really difficult. I'll just say, well, let's write this code and then I'll talk more. So go ahead and try to compute the adjoint of SZ and store it to the variable SZ underscore adjoint. I didn't mute my screen. Anyway. It's fine. Okay. I just wanted to pull up this meme because I just felt like I should make one for this method of testing. But it's sort of like, yeah, we can like print the values and make sure visually inspect that they're okay, and then like subtract off what we expect, and then like do the assert NP all close. That's like this level. I didn't make the meme. I wish I would have. It would have been a lot cooler if I did. Anyway,
For Wednesday.
for Wednesday. So let's go ahead and run this line of code. So we're going to compute SZ adjoint as sc.conj.t, and then print np.allClose SZ adjoint comma sc, and I get the number true. I get the value true. So this, what type of data is this, by the way, or what type of variable is true? Anybody remember? Boolean. Yes, wonderful. So I get true. Did everybody get true? Anybody get false? Okay. Great. So yes, what was I going to say? So this all close. So for numbers, comparing numbers in a computer is treacherous business because there's finite precision that the computer can really use to represent any given number. So these comparing SZ to its adjoint would probably be fine. They would probably look equal, exactly equal to a computer. But a lot of times with computations, you know, you've got these factors of h bar in here, which are like 10 to the minus 34, and then you've got other numbers like speed of light, which is like, what, 10 million, something like this, 10 to the 8, 10 to the 6, whatever. So there's a lot of round off error that happens. And if you just end up with two numbers that you've computed through different routes, and you say like, please computer, tell me, is this number exactly equal to this number like I expect it should be? Oftentimes that is not going to pass for you because there is imprecision in one of the numbers, which is different than imprecision in a different number. So this all close is quite handy, or is close, are two different Numpy functions for comparing single values or for comparing lists of values, which is quite handy when you know that you have finite precision in your data. Okay. Anyway, I think that's probably a good place to end. So there's the next few blocks, we actually have some questions, but what I'm going to do is actually use Friday's problem solving session to take you all through this a little bit more. We'll actually be back here. And will you be able to join us on Friday? Okay, great, wonderful. So then we will kind of just keep this file. Make sure you have saved it. Make sure you can find it in your Google Drive.
And then, in order to help grade, please make us editors.
Oh yeah,
right?
yeah,
Is that how?
yes.
You guys
Yeah.
have-
Ultimately, when you send us, you will change anyone with link to editor, and then copy the link and send it. Or how do you want them to submit it?
You'll be